Y'all look like you could use some good news. How is this for good news? This is the last class before spring break. So I'm canceling class Wednesday and I'm canceling class Friday. There's a few reasons for that. One is, if you recall, one of the things that I stated at the very beginning of when we first started discussing shear is that when we finish shear, that's it. We're going to call it until we come back from spring break. I'm not starting serviceability now. I'd rather wait until we come back because if I start it now, you're going to forget it anyways. Two, senior design has got a somewhat intense day on Wednesday, so figured cut those folks some slack. So I figured this was an all in all a reasonable avenue. Now, let me show you what we're going to do today. We're going to do a shear design example, and we're going to do it according, the loading is going to be different. We're going to have concentrated loads. Now, I want everybody to look up here. I have the solution. And I'm going to hand you the solution out here in a second. And I'm going to pull it up on the screen. I'm actually going to go analog today for a little bit, and I'm going to use the marker. I want everybody to sort of pay attention. You don't really need to write a lot of this down because it's all right here. I mean, you can if you want. But I want to go through some issues associated with this example together, like as a group. And then we will go through the example, sort of the detailed example step by step. Does that sound good? I think that'll make it, you'll understand it a little better, and it'll make it go a little faster. Okay? So first off, here's the example. Okay? Here's the example. Now, this example is obviously a little different than what we did last time. So last time we had a uniformly distributed load. So here's our example last time, and here's our example this time. Now let me ask you, what is going to make this look like, what happens? Like, why is this example going to be different? When you see this, what's the first thing that you think is going to look different than our previous example? We have concentrated loads, so what is going to look different? The shear diagram, right? It's going to be a different shear diagram. So what I'm going to do on the board is I'm going to start to illustrate what's going on with that shear diagram a bit, and then I'm going to give you the solution. Okay? So don't worry, you'll get the solution and you'll get everything that you need, but let's go through this together step by step. Now, first off, everything here is factored. Okay? So we're going to break this, we're going to go back to structural analysis land, to CE 312, right? All right? All right, so we have a beam with a point load here and a point load here. And then we have a hinge and a roller. Now this distributed load is 4 kips per foot, and this is 20 kips, and this is 20 kips. Now, before we start breaking out any of the statics or anything like that, let me ask you a question. Is there something that you can tell me about this structure in terms of dimensions and whatnot? Now, well, first off, we're going to have a reaction here and a reaction here. And then let's put some dimensions up here on the board so that we have that. So this is 6 feet, 6 feet, 6 feet, 6 feet. Can somebody tell me anything about the layout of the structure? It's symmetric, right? So in other words, this reaction is the same as that reaction. Would everybody agree with that? Can anybody tell me what that reaction is? So, break out your Casio FX115ES pluses and tell me what that is. Y'all know the drill. Come on now. So, can anybody tell me how to compute it? Can anybody tell me what the formula is over here? First off, let's take the point loads. we have two 20 kip loads divided by 2, so just one of them, right? Plus, tell me what to write. I'm asking you. Is everybody okay with that? I mean, if you're not, tell me. Everybody good? What does this come out to be? So this is 68, and this is 68. Okay, everybody good? Now, we've got our reactions. Now it's time to draw our shear diagram. Keep in mind, all these loads are already factored. So I guess I can say that this is a V sub U diagram since they're already factored because the point loads are PU, they're factored, and the distributed load. So tell me what to do. Go up 68. So maybe right here, call that 68. Now what do I do? Now hold on. What'd you say? Okay, go down to 44. Why are we going down to 44? So this line is going to go down like that to 44 because that's 4 kips per foot over a distance of 6 feet. Is everybody okay with that? Then we're going to drop down 20 to 24. Would you agree with that? Okay. Then it should be sort of flipped and inverted, sort of mirrored, right? And so this is going to be minus 24. That right there at midspan is going to be 0, right? Then we go down to minus 44, and we go down to minus 68, back up to 0. Would you agree with that? Any questions? Okay. Now, what I'm going to do over here is I'm going to blow this up. Okay? I'm going to blow up this left end. I could work with the right end. It doesn't really matter. I mean, it's the same, just flipped. I'm going to work over here. I'm going to blow this up a bit. So there's nothing over here that I'm drawing that you're not seeing over there. So we, that, actually, hold on, and then that. We'll sort of redo that a bit. Okay, that's good enough. Try and keep this organized. So this is 68. This is 44. This is 24. And this is 0. And to be clear, these distances are the same at 6 feet. Would you agree with that? Now, this looks different than our shear diagram last time, right? This was our shear diagram, or this was our loading from the last problem. And on the last problem, when we blew up the shear diagram, it just went up and went down, right? That was our shear diagram, right? Because it just, if we looked at the whole beam, it looked like that. Well, the reason why that's relevant here is because on our last problem, we only needed one equation to plot the shear diagram, right? Remember, we had like VU was something like 115 minus 11.5x. Do you remember that? We only needed one equation. Well, that's not the case here. We need 2 equations, right? Because our shear diagram occurs in pieces. Like we have a shear diagram that goes from x equals 0 to x equals 6 feet. But once we get past 6 feet, we have a new curve, right? A new line. So this shear diagram is not going to be defined by one equation. It's going to be defined by two. Okay? Now, regardless of which equation we're looking at, this one or this one, both of these lines share a common trait. Does anybody know what trait is common for both of those lines? The slope. What is the slope of those two lines? -4. Why is it -4? What's that? But why -4? Because that's the load, right? Remember from structural analysis, the value of the load is the slope of the shear diagram, right? So for both of these lines, the slope is -4 kips per foot. Would you agree with that? Okay, now let's take this first line, this one over here. What is the y-intercept of this line right here? 68. So would a fair statement for this line is that VU is 68 kips minus 4 kips per foot times x? Would that be fair? That's right, isn't it? Now, here's the kicker with this one. What is the y-intercept of this line? Can anybody tell me? 48. Do you see how? Watch this. See, what we're after is that. And see how that's 48? So this is 48 kips minus 4 kips per foot times x. Would that make sense? Any questions on that? And so for each of these, what I can then do is I can say, all right, x for the first one is going to be 68 kips minus VU over 4 kips per foot. And then this one is x equals 48 kips minus 4 kips per foot, or sorry, minus x, or minus VU, sorry, minus VU. And then that. And so this one is only going to be from x equals 0 feet to x equals 6 feet. And this one is going to be from x equals 6 feet to x equals 12 feet. Is everybody okay with that? Does that make sense? If it doesn't, please tell me. Okay, all right. If that makes sense, then I'm going to pass this out. Which, by the way, if you go onto Blackboard, this is uploaded. If you go to the lecture notes section, there's a PDF of this. There you go. All right. Now I'll lower the lights so the screen comes up a little easier. All right, because what I do on this example, there's a couple of things that I sort of just like do, and sometimes you might be thinking, well, why did he do that? Well, full screen. Okay. First up, okay, so here's our example, and what we're trying to do is determine the shear stirrup layout. Now, up top, I have my system parameters. Everybody's like, what's that? Ah, no. So I have 3 KSI concrete that's normal weight, so the lambda value is 1. I have a beam that's 10 inches wide and has a 20-inch effective depth, and it's a 24-foot-long beam, although that doesn't really matter. What really matters is this. This is the loading scenario. I have a beam that's 24 foot long, that's simply supported, that has a distributed load of 4 kips per foot, but I threw in those point loads as well. Now, if you're wondering physically, where would point loads actually come from? They'd come from beams framing into this element, right? Remember the hip bone connected to the leg bone, the beams frame into the girders frame into the columns frame into the ground. This is probably some girder element where there are some floor beams coming in. And those floor beams have a reaction of 20 kips. That's where this is coming from. All right? Now, since the loading is symmetric, I determined the reaction the same way I did up here, and I got 68 kips. And then you can see I drew the shear diagram. Now, what might be a little strange on the shear diagram is why did I connect this dotted line here to 48? This is why, so that I could determine the equation of these two lines. So this line has an equation of 68 kips minus 4x, and this one has 48 kips minus 4x. And it's because all the linear portions of the shear diagram have a slope of negative 4 kips per foot. It's negative because the load is going down, and it's 4 because that's the magnitude of the distributed load. Okay? So, yes?
Do we have any worry about like the equations in line for when it's under 0?
No. And give me a second, I'll show you why. You'll see what's going to happen here in a second where, let me say this, there is an instance where you have to consider something there, but it's not what you're thinking. And I'll show you here in a second. Is everybody okay with this? Now, this is the shear diagram, and so I remember, when you're constructing the shear diagram, you might think, well, okay, great, you got the shear diagram, that's good. But remember, there are 3 values that we need to determine, that we need to plot on this shear diagram. Remember, one is VU star, and one is phi VC, and one is half of phi VC. Y'all remember that? So remember, phi VC and half of phi VC tell us our bounds as to whether or not we actually need stirrups, and VU star is where we can start using, or where we can start our design. Now let me scroll down a bit. Now, what I've got here is the computation of phi VC and half of phi VC. So VC, we start off with that, is 2 lambda BWD square root of FC prime. So 2 lambda BD square root of 3,000 PSI. Remember, you put in PSI and you get out PSI. And so when you compute this out, remember 2 times 1 times 10 times 20 times the square root of 3,000. That'll give you an answer in pounds. Okay? Now, we want an answer in kips because all of our loads all over here, they're all in kips. So I convert that to 21.909 kips. That's VC. So I multiply by 0.75 to get phi VC, and I multiply by half to get half of phi VC. So that's obviously a lot faster than we do this in class because I go through and chug it out and have everybody second the values. Do I need to do that? I mean, is everybody okay with that? I would think that that's pretty simple at this point because it's really no more of a different method than the last example, just different numbers. Sound good? Okay. Now, here's where things start, you got to start making, some logical sense. And so I don't have it here on the screen because I really want to make this to make sense. Okay. Now, we have phi VC and half of phi VC. Now, why did we compute those? Because we want to determine where they are on the shear diagram, right? So we're trying to determine x at phi VC and x at half of phi VC. Now the question, which equation should you use? This one or that one? The one on the left or the one on the right? The right. Why? Exactly. Phi VC is 16 kips and half of phi VC is 8. So that's going to be somewhere like here and here, right? So the equation that we use to determine x at phi VC and x at half of phi VC is this equation. Does that make sense? Because this is 16 and this is 8. Look at your shear diagram. That's 24. That's 0. So would you agree that that's going to be here to here? So you would use this equation to determine x, not that one. because this equation is only valid for this range. Does that make sense? Is everybody okay with that? Now, those are two values that we need to determine for the plot. What's the third? We've got the x at VVC, the x at half of VVC, and what else? VU star. Now, what is VU star? It's the shear D away from the support. What's D? And for this problem, 20 inches. So this is 6 foot long, so 20 inches is going to be somewhere about like right there. Would you agree with that? So which equation do we use for shear? This one or this one? The first one. So this is the one we use for VU star. Everybody okay with that? So down here below, if you look at VU star, I say VU at x equals D, and I'm using 68 minus 4x. Why am I using 68 minus 4x instead of 48 minus 4x? Because that's where D is. D is in this range, not in this range. Any questions on that? Okay, so that's for the VU star, whereas when I plot out x equals VVC and x equals half of VVC, I use that equation because that equation is where VVC and half of VVC is going to lie. Is everybody okay with that? Yes? Exactly right. So the question was, what if VVC is like 30 kips? And so that's sort of what I was getting at here with you is, what if VVC was like 30 kips? Well, you wouldn't use one equation or another. You would just say it's right there. Does that make sense? And that's something to pay attention to, because if you just, this is really important. If you just start blindly using equations, like, well, that's what we did in class, I just need to change the value and use the equations, you're going to get some weird answers, okay? It's possible, you start solving for x with some of these instances, you get negative values because it's the wrong equation and you're trying to compute values all the way out here. Remember, the equations are only valid for the ranges that are specified. Does that make sense? Okay, so when it's all said and done, your shear diagram should look like this. Okay, so it's basically this diagram. Remember, it's cut off right here. And this is, instead of 68 kips, it's 61.333 kips, because that's VU star. And our VVC is right there. And half of VVC is right there. Everybody okay with that? So, maintaining your proper unit conversions. Remember, we have 3 regions. We have the region anywhere where the shear is bigger than VVC. This is where we absolutely, desperately must carry stirrups. We have the region between VVC and half of VVC where the concrete carries the shear, and then anything less than half of VVC where we don't need stirrups at all. Okay? I'm actually going to reproduce this on the board over here. It's kind of messy over there, and I kind of want a bigger diagram because you'll see why here in a sec. Okay, so this is shear, and this is X. Okay, this right here, that's VU star, which is 61.33 kips, and then I have VVC, and I have half of VVC. My scale is probably a little off on the board, but that's okay. Okay, And so this point right here, that's x equals 20 inches. This is x equals 72 inches, and that's what I'm talking about is where that point load is. This is x equals 94.7. And this is x equals 119.4. And where that crosses right there, that's x equals 144 inches. Why is it x equals 144 inches? How long is the beam? No, it's 24 feet, so half of it's 12 feet. And 12 feet, so yeah. Okay. So we need to place stirrups anywhere between x equals 0 and x equals 119.4 inches. Sound good? Okay. I just wanted that up there so that we would be able to reference it as we go through the example. Okay. So we've got our shear diagram constructed, and so how do shear stirrup layouts work? Well, remember, up until now we've been placing our first stirrup at 2 inches, and then we start placing stirrups, let's say, at 4 inches until we stop needing it. So here's what I'm going to do. I'm going to start off by determining the starting S value at VU star. Okay? So that's, starting at this point right here at the very beginning of the beam, what would be the stirrup spacing required right here? Okay? And so we use that VU star value. Remember, I'm just taking my phi v n expression and solving for S. Plug and chug. Make sure that your units are consistent, because I got inches squared, KSI, inches, kips, so it's all kips and inches. Plug and chug, and I get 4.41 inches. So that means that, remember, when you're selecting stirrup increments, you don't round up, you round down, right? So if I had 4.41, that doesn't mean we'll use S equals 5. That results in a weaker beam. Use S equals 4 inches. So if I wanted to determine my design, it's probably going to be something like this. I'm going to have one stirrup at 2 inches, some number of increments at 4 inches, and then some number of increments at S max, right? And that's going to be how I determine my stirrup layout so far, right? That's if I only use 4 inches and S max. Is everybody okay with that? Or am I going too fast? Okay. But now the question is, what's S max, right? Well, let's determine that. So we've got our S required. What's going on with our maximum S value? Well, we say, all right, we determine S max 1, which is the minimum of D over 2, or 24 inches. So D is 20, so 20 over 2 is 10. So that's 10 inches. And S max 2, remember we take 0.75 square root of FC prime, and that comes out to be like 41. And so we take AV over FY divided by BU, and then times the maximum of whatever this is, or 50, came out to be 50. So 0.22 times this divided by 10 times 50. Make sure you're consistent with your units, because this FY has to be in PSI, this has to be in PSI, and it comes out to be 26.4. So between these two, the maximum's 10 inches. Is everybody okay with that? Did I go too fast? Everybody good? Okay. So here's the deal. I propose that our design, at the very least, should look something like this. We're going to start our first stirrup at 2 inches. We're going to have so many spaced at 4, and then we're going to have so many spaced at 10. Okay? Well, how do I determine that? See, theoretically, I could put one stirrup at 2 inches and then just use this 4-inch spacing everywhere, right? Okay? But that wouldn't be economical. Instead, why don't I try and figure out when I can start using this S equals 10 inches? Okay? And so how do I do that? Well, let's look at how strong that is. So let's determine the range for S equals 10 inches. Okay? So if I were to use a 10-inch spacing, what do I get? Well, V sub S is AV FY D over S. AV FY D over S. Okay? So that comes out to be 26.4 kips. And then PVN is PVC plus PVS, plug and chug, and I get about 36 kips. Is everybody okay with that? Now here's my shear diagram. Remember, this is 44 kips, and this is 24 kips. So where does this value occur on the shear diagram? It occurs right here, okay? That's where it occurs. And so if you start, this is where this shear diagram becomes invaluable, okay? If you just start blindly looking at the equations and not actually looking at the diagram, it's very easy to try and solve for x at this point. And if you try and solve for x, you're going to get a value that doesn't make any sense, okay? Where does 36 kips occur on the shear diagram? Right there, okay? So if you want a verbal description of this layout, here's what it's going to be. Place first stirrup at x equals 2 inches. Then what we're going to do is use 4-inch spacing until x is 72 inches. Then what we're going to do is use 10-inch spacing until where? Where? Until x is 119.4. Because that's when we don't need stirrups anymore, right? Because once we get past that point right there, all those shears are less than half of PVC, and we don't need stirrups at all. Make sense? So how would we lay this out? Well, I've got one at 2 inches, so how many do I need at 4 inches? I'm asking you. $18, right? Look, you can look at the page, but I want to make sure, because I could be wrong. I'm not perfect. I could be wrong. So this is 18, which is 72 inches, because right here, that'll get you to x equals 2 inches. This will get you to x equals 74 inches, right? If you used one less, that'd be x equals 70, and it isn't far enough. Now, if I'm at x equals 74, how many do I need to get at or past 119? Well, 84, 94, 104, 114, 124. I'm thinking I need 5. Right? And so that is 50. And so that's 18 and 5, 23. That's 24 stirrups at 74, 124 inches. Or 48 stirrups total. What do you think? Okay? So that's what I've got right here. Now, what you could do is you could try and improve this design. You could say, well, I'll tell you what, how about this? What about increments in between? Well, I've got 4-inch spacing and 10-inch spacing. What about something in between? What about 6-inch spacing or 8-inch spacing? Well, first off, using the 8-inch spacing actually makes 0 sense at all. Because if you use 8-inch spacing, the VS is 33 kips, the PVN is 41.182, and that's in between this range as well, right? So what we would do is we would place the first stirrup at x equals 2 inches, and we use 4-inch spacing until x equals 72, then we'd use 8-inch spacing until x equals 72. We wouldn't have any stirrups in there at all. So really the only way that we can improve this, I would say easily, is to use 6-inch spacing. And so the way that our layout would change is we would say, all right, let's use 4-inch spacing until x equals, what, 55.7. Then use 6-inch spacing until x is 72. And then use 10-inch spacing until X is 119.4. And by doing that, we were able to shave like 2 stirrups off the beam. Not a lot, but we did trim it down a bit. But there's a point where you could use, all these different increments of stirrup spacing, and you really aren't going to, generate overall economy. There's a point where it just stops mattering. So, I lost my marker. Any questions? Yes. Okay. You have this? Well, you do. It's right in front of you. So, it's just sort of a simple way of ensuring that we have a stirrup that crosses the support. So watch this. So let's say here's a beam. Right? And I use 4-inch spacing everywhere. Okay? That's enough. I don't really feel like drawing anymore. Okay? Now, that beam goes on forever, right? What I'm going to do for a problem like this is I'm going to place my support like here, right? So that's where the support condition begins. So this is 4 inches, this is 4 inches, this is 4 inches, and goes on forever. But right here, that's 2 inches. Okay with that? The reason why we start that first stirrup at 2 inches is to ensure that we have that stirrup spacing that goes across the support condition. So 2 inches is common, half of S is common. Well, either one is fine. So essentially what we're doing is, here's the beam, right? And the support starts here. So that's X equals 0. The problem states that we have to start out with S equals 4. So the way that we do that is we place that first one halfway over, and then we have S equals 4. Because the idea is that if we had one back here, then that 4-inch spacing goes past the support. That's why. So, does that make sense? That's a good question. Any other questions? Now, this was a different way of doing this example in class. Is this okay? Because this is me just sort of giving you the answer as opposed to going through and doing the math. But honestly, I felt that since we've done a shear example before, the only thing that really changed was the 312 stuff. So I figured it was a way of making it go a little faster. So, any questions? All right, so here's the deal. Okay, this homework is due on Friday, and we're done with shear. I don't really have anything else to talk about because that's basically it. So here's what we'll do. On Wednesday, we're not going to have class. I'm not going to come in here and start teaching another topic. Instead, what I'll do is this. If you have questions about homework 6, I'll come down here at 10 o'clock. If there are people here, we'll talk about homework 6. If not, I'm going to go right back up to my office. As for the homework is due on Friday, but it's due on my cart, okay? In the interest of not making spring break last, or the wait before spring break last any longer than it should, let's make the homework due at 10 a.m., which is right when class would be, when it would be due in class anyways. So 10 a.m. on the cart, outside my office, you submit homework number 6, shear design. When you come back from spring break, we discuss serviceability. Okay? Sound good? All right. That is pretty much all I have for up until now. One thing, before we close, let me pull up the schedule. Because I want to make sure I'm correct on something. Yes. Say that again. Oh, yeah, I have no problem with that. I have no problem with that. Yeah, if you want to turn the homework in early, you can. Okay. When we come back from spring break, I want to make sure that everybody's clear on the schedule. We start deflections, okay, which is, when I say serviceability, I'm basically talking about deflections. So we've done moment, we've done shear, so deflections come next. Let me explain a couple things real quick about deflections. So first off, deflections are going to utilize two values. One is the gross moment of inertia. So if you have a rectangular beam, remember how that's BH cubed over 12? All right. But it is also going to utilize a cracked moment of inertia. Remember how with the cracked moment of inertia, you take a beam that has reinforcement like this, and you turn it into a beam that's cracked, and then we turn that steel into an effective lump of concrete. Do you remember that? Well, that's going to show back up when we look at deflections. Okay? What I'm going to do, the day you come back, I'm going to assign the homework on deflections. The actual computations are pretty straightforward. It just involves this and this. Like if I gave you the gross moment of inertia and the cracked moment of inertia for a problem, I can teach you everything about deflections in a day. The only thing that takes a while in class is this. Okay? So it's just something I want to prepare you for because we are going to see this again. So when we come back from spring break, I'm going to assign you homework number 7 on deflections. Okay? It's going to be due the following Monday, and then we have the exam on Wednesday. Okay? The exam covers shear and deflections. I knocked the marker over again. So that's the exam. Remember, homework number 5 on T-beams and doubly reinforced beams is not covered on any exam. Okay? I'm not putting it on an exam because it's just the same thing as what we did before with bending, just more of it. So I already examined you once, not doing it again. Any questions? Everybody clear on housekeeping? Well, then, since just about everybody is in steel anyways, I'll see you here in a few minutes. But in terms of concrete design, so long for the next 2 weeks. What?